Hi, everybody. Yeah, it's a great honor to be doing a keynote at CppCon. It's very special for me. This is the first conference where I ever gave my first conference talk ever. That was 7 years ago. So this is a very special place for me, and thank you so much for having me. And thank you so much for coming. All right, so who am I and why am I talking about C++? I kind of do 3 different things that have to do with C++. The first thing is obviously my job. I'm developer advocate at JetBrains. We make developer tools, including for C++ developers, such as the C-Line IDE, ReSharper C++, which is our Visual Studio extension. We also make Rider, which is our .NET IDE, which is also great for Unreal Engine game development. So that's all really cool stuff, really cool products. The second thing that I do that has to do with C++ is I've spent about a decade of my career doing audio software, in particular music production software. So this is, Cradle is a company I co-founded a couple of years ago. And this is one of our products that we released this year. It's called the God Particle. Here you can see it in action. It's a mastering plugin. And this is all kind of audio real-time processing. So there's lots of C++ going on here under the hood as well. And the third thing that I do is I have been a member of the C++ committee and kind of active there and writing proposals since about 2016. So this is not as long as some other people. There's some people on the committee who have been there for over 2 decades. So you're not going to find me on any of these older pictures here. However, you will find me on the most recent 2 from COSS 17 and COSS 20. And this last picture here was taken at the last in-person committee meeting that we had, which was in Prague in February 2020, and that's when we completed work on C++ 20. And that was just before everything shut down and we had to start doing everything remotely. And as you all know, and I don't have to tell you that, a lot of stuff has happened in these 2.5 years, right? But one of the things that happened, and that's something that actually happened relatively recently, 7 weeks ago, at the last virtual plenary meeting that we had at the end of July, C++ 23 is now feature complete. So that is really cool. It's not done yet. We still have 2 committee meetings and about half a year to kind of fix bugs. It's called ballot resolution in ISO language. But we're not going to have any more features to add to it. So we kind of have a really good idea at this point what the scope of the new standard is going to be. So it's a great time to be talking about it. And so as I was preparing this talk, I was thinking, OK, which aspects of C++ 23 should I be talking about? I kind of looked back a little bit on a few talks I've done here earlier. This is a talk about C++ 20 I did here 3 years ago, where I mentioned something like 20 or 25 different features of the new standard, which was 2020 at the time, in like an hour. And it was a really fun talk, but I thought it's a little bit superficial. You're kind of rushing through it. And I wanted to go kind of a little bit deeper. And what do I mean by that? The way I see C++, it's basically just a giant toolbox, right? So you have your saws, you have your hammers, you have your screwdrivers. If you look at the screwdrivers, you then have Phillips screwdrivers, you have slotted screwdrivers, you have Torx screwdrivers, and then somebody goes and adds a pentalobe screwdriver, right? Which is really great for turning pentalobe screws, which is a particular problem that you will run into if you're doing a particular kind of thing in a particular case. And it's very useful for that, but it's not going to be something that a lot of people are going to end up using. And it's not going to change the way you think about screws, right? So, and it feels to me that a lot of the features that we keep adding to the standard are kind of like that, right? They're kind of specialized things that let you solve a certain problem. And what I'm kind of more interested in is features like the cordless electric screwdriver, right? Which before you had to turn screws by hand, and now you can just go bzzz, right? So, and that's going to change how you work with screws. It doesn't matter what kind of screws you're using. It doesn't matter what job you're trying to do. It's going to be very, very useful for a lot of people. And so this is kind of what I'm looking for and what I'm interested in. And then I did another talk 2 years ago about, again, C++ 20, where I was kind of looking at those kind of features. And I ended up talking about the big 4 of C++ 20, which obviously many people have done talks since then about those. Coroutines, concepts, ranges, and modules. And those features are kind of they fundamentally change the way we think about C++, right? So they change our mental model of functions, templates, algorithms, and how we compile and distribute our code, right? So they're very, very fundamental things, and I talked about that in that talk. And C++23 doesn't quite have stuff of this big kind of magnitude, this kind of very fundamental magnitude, because C++23 is kind of a bit of a smaller release. Its mission is kind of to complete C++20. But I would argue that there are still a few features in C++23 that are going to be, very influential and very useful for kind of the average C++ developer and for a lot of people. And so there is some stuff in there which is kind of that kind of category, I would argue. And so let's see if we can figure out what these are. If you go to cppreference.com, I'm sure many of you know this page. There's this page, C++ compiler support, which tells you which features are supported by which compilers. And it already has a table of everything that we voted into the C++23 committee draft. So there's a complete list there. And it's a long list, actually. So here's all the core features that are in C++23. And it's a long list. And you keep scrolling. And then there's an even longer list of standard library features that are new in C++23. And the list goes on. And the list goes on. So the committee has done actually quite a lot of work in the last 3 years. If you zoom out, it's a really, really, really long list. And so the leftmost column is kind of just the list of new features, basically. And interestingly, almost half of those is just stuff that we approved at the last plenary session at the end of July. So what I want to do is I want to now take all of these features on the left-hand side and kind of break them out into a slide. And they don't actually fit on a slide. So this is one slide with just the language features. And then there's 2 more slides with all the library features. And so what we need to do is we need to kind of whittle this list down a little bit and remove things until we arrive at the really kind of interesting, really fundamental, really influential bits that we then are going to talk about. And so it's kind of a completely subjective selection criterion as well that I'm going to apply here. It doesn't mean that, not all of the stuff is super interesting and super useful. It just means that I'm not going to talk about it today. So let's try and reduce this list a little bit. So first, I'm going to single out all the defect reports, deprecations, undeprecations, clarifications. I'm going to say that, this is really good work, but I'm not going to talk about this today because they're not new features, really. So I'm going to remove them from the core language list, and I'm going to do the same for the first and the second page of the library features. Next, we're going to go back to the first page of the library features, and I'm going to remove everything that's kind of tweaking stuff. So kind of adding no except here, adding const expr there, adding a new constructor or a new constraint somewhere, this kind of stuff. Cool stuff, makes it easier to work with these features. Not going to talk about that today. Page 1, page 2. OK, so the list gets a little bit shorter. And then there is a huge bucket of additions which has to do with ranges. So this is the first page, and this is the second page here. All the gray stuff is ranges-related stuff. And you can see that a huge amount of work has gone into ranges. So this is really, really awesome. However, I think this should be better covered by a dedicated ranges talk, because it's kind of its own subset of the language, which has been growing quite substantially recently. But it is in addition to something that we started in C++20. It's not a completely new direction. So even though this is amazing stuff, I'm not going to talk about it today. And then there's another remarkable kind of bucket of features in C++23, which is everything that has to do with kind of Unicode, character encodings, text, that kind of stuff. And so a lot of work has gone into those things as well. We have a study group for this, SG16, which has to do with Unicode and text. They've done a great job. They've fixed a bunch of stuff. There's quite a few people who were doing this work, but I just want to mention one person, Corentin Jabot, who wrote a lot of papers on this subject. He has given a lightning talk here on this stage 3 years ago, which was called Text. And if you have not seen this lightning talk, I highly recommend you to watch it. It's one of my favorite lightning talks ever. He convinced me that text is very complicated, and according to him and other people, Text is still kind of broken in C++23, so we're not done yet. So maybe it's not quite yet time to give a keynote about text in C++23. In any case, Quarantine would be a much better person to talk about this than I am. So I'm going to remove the kind of text-related stuff as well. And now we go back to the kind of other core language feature. These are kind of tweaks or improvements of existing core language features, which you will kind of discover, I think, along the way. So this is kind of stuff that just makes it easier to write something, avoids you to write boilerplate that you don't need, lets you write things in a more elegant or simpler way. For example, we have CTAD, which we have kept improving over the recent standards. And now you can get class-named with argument deduction from inherited constructors, right? So you don't need to write deduction guides anymore. You can now inherit them. And this is something you kind of find out as you work with that. And another thing, for example, is lambdas, right? If you don't have any arguments, you don't have to write paren. But if you add mutable, then you do have to write paren. It's kind of weird. Now you don't have to do that anymore. So these kinds of simplifications, kind of sanding off the rough edges. Another one that I do want to explicitly mention here is the multidimensional subscript operator. So that's the square bracket operator, which can now have multiple arguments. So that's an interesting one. We're going to talk about it later in another context. But for now, let's remove all of these kind of sanding off the rough edges kind of features from the list. And now you see the list gets quite a lot shorter already. And I'm going to do the same here with I'm going to do something here with the library features and also remove everything that's kind of an improvement of an existing feature or something that's kind of adding to an existing feature rather than being a new feature in its own right. And I'm going to do that on this page, and I'm going to do that on the second library feature page. And now we have quite a lot fewer items, so everything now actually fits on one slide. So now we're down to one slide full of language and library features. It's still a little bit too much for a keynote, so let's see if we can whittle this down a little bit further. So we have here hash warning and hash elifdef and elifndef, which is something that is new in the standard, but Clang and GCC have been supporting it for ages already, so it's not really something new, so I'm going to remove that. We have this one here. It's kind of a C compatibility feature, so again, nothing completely new. I'm going to remove that. This one, if const eval, is cool, but arguably it's kind of cleanup from C++20 when we introduced it as constant evaluated. So I'm not going to talk about this one. This is cool. We now have a literal suffix for size t, and the suffix is z, so that's that. That's cool. We talked about it. This one, very cool for kind of numeric stuff. We now have kind of fixed with floating point types like std float 16 underscore t and float 32 underscore t. So they're a little bit similar to the fixed with integer types like uint 32 underscore t, except that the integer ones are typedefs, whereas these are kind of new types. Super interesting, fantastic topic for like a numerics talk. Not going to talk about it today. This one is also really interesting. When I was looking at everything we've approved, I thought when I looked at this one first, this is kind of a tweak. It seems like it's kind of a niche thing, like you need this in kind of specialized, very specialized kind of cases. But then I was talking to my friend Gaspar Asman, and he actually pointed out to me that this feature opens up API design in like a really, really interesting way. And he was really excited about it, and I thought, okay, this is cool. I need to look into this a bit more. But that was literally last week, so I didn't have time to do that yet. So I don't yet understand kind of really the full impact of this particular feature. So I need to go and kind of look at it more because it is actually apparently quite interesting. But I haven't done that yet, so I'm not going to talk about it today. And here's another one. This is actually something that's very close to my heart. This is something that I have spent almost 3 years now standardizing, portable assumptions and attribute assume. This is an attribute which lets you basically tell the compiler to optimize based on certain assumptions. This is great if you do anything like low latency, real-time stuff where every nanosecond counts and you want to help the compiler kind of get the optimizations that you know it can do, but that the compiler cannot figure out on its own. And if you're doing these kinds of low latency applications, that is really, really useful to have. But the downside of that is that it's really, really easy to kind of introduce undefined behavior. So this is really a kind of an expert-only feature. Something like, I don't know, atomic memory orderings or something like that. So if you do need it, you know you do need it. but I would say that most developers shouldn't touch this because it's a very dangerous feature. It's very easy to introduce undefined behavior. And the same is true for this closely related library feature still unreachable. So I'm not going to talk about those today. And then there's a bunch of more features here, which I would say they're maybe not dangerous or anything. They're very useful, but they're kind of specialized. They're these like pentalobe screwdrivers, right? They're like solving a particular problem that you might have, and then you're going to reach for that tool. But I would say that even though they're great, they're kind of specialized. And so I would say most developers will probably not have to deal with most of those features. So even though they're great, I'm going to just say they're not like the most kind of influential features that are going to have an impact on a huge number of developers. And now we are left with this much shorter list here. And this is kind of really the meat. This is, I would say, these are the really big new features in C++, in C++23. And so we have standard library modules, which Daniela Engert talked about on Tuesday, and we also have some first library support for coroutines. Arguably, this is completing C++20. This is something that we should have probably done in C++20. So I'm going to remove that. This is kind of leading on from C++20. And then we have these four. And they're really, really great new libraries. And if you need them, you will reach for them and you will use them, and it's going to be great. But they're kind of very self-contained. If you want to do this thing, you're going to reach for this library. But it's not that they really touch anything much kind of around them. So they're kind of relatively self-contained. So I'm going to say, let's remove those. And now we're left with these four. And these four features, in my opinion, very completely subjective opinion, are the four most kind of important features of C++23 in the sense that they're going to have a huge impact on how we write C++, how we think about C++, how we learn C++. And they're kind of touching different areas, and they're going to probably be relevant for quite a few C++ developers. So the rest of the talk, I'm going to talk about these four. And I'm going to start with deducing this. So deducing this is by far the biggest new core language feature in C++23. It's, here's the paper, four authors, Gaspar Asman, Sai Brandt, Ben Dean, and Barry Revzin. This paper has been in development for quite a few years. Ben told me that he started thinking about this problem around 2013, and some of the other authors were also thinking about that problem kind of at the same time, and then they joined forces. The paper went through quite a few iterations, and now it's in the standard. Ben actually did a brilliant talk here last year about deducing this, called Deducing This Patterns, which is just kind of 1 hour just about this feature. So obviously I cannot go into quite as much detail. But I would say this is, so far, from what I've seen, the ultimate kind of reference on this feature. So if you want to dig a bit deeper, I recommend you watch this talk. I'm going to talk about it not quite for an hour, but I'm going to try and mention kind of the most important or interesting things that you need to know about it. And one of the reasons I love this feature is because this is something that Bjarne said, when we're talking about like what features we should be adding to the standard. Is this worth adding to the standard? And he said, it's probably a good proposal if it solves at least two unrelated problems at the same time. And it turns out deducing this is actually a really good example of this because it solves at least 3 problems and probably maybe even 4 or 5 problems. So the actual change in the language specification is actually really small, but it has a huge impact in all kinds of different areas. So what is deducing this? Why is it so relevant? Some kind of C++ class, and as we know, we can overload member functions of a class on whether or not the object itself that you're calling this member function on, this object, whether or not it's const or non-const, okay? So this is hopefully not news to anybody here. We can overload on that. Slightly less frequent, we can also overload on whether an object is an L value or an R value, right? This is something we can do since C++11, and we use these ref qualifiers to do that. And you can also combine them and overload the same member functions on like all 4 combinations of these properties, right? And so at the very first level, what deducing this does, it gives you a different syntax to express exactly the same thing. So here, we're talking about whether this object, which is the kind of implicit first argument of every member function, whether that's const or ref or something, but like you specify this with this weird syntax kind of at the end of the declaration, right? So what deducing this allows you to do is kind of allows you to write it in this different way, where you now make this implicit first, this argument, explicit. And you write it literally as the first argument, and you mark it by putting this keyword this in the beginning. And now you can write it like a regular argument, and you can specify with the usual parameter declaration syntax whether or not this implicit first this argument, that the object itself, whether that's const or not const or ref or ref. And so this is exactly the same as the stuff on the left-hand side. It's just a different syntax for the same thing. However, now we're using regular kind of parameter declaration syntax, so we can give this argument, this parameter, we can give it a name, right? Self, I think, is a good name. This is what Python people use, so probably a good idea. So that's what you can do, but also you can do something more interesting. Because this is now following kind of the usual rules of parameter declarations, we can now, instead of declaring 4 overloads, we can declare 1 template. And that's going to now follow the usual rules of function template argument deduction, which we had since the 90s. So we can now template on the type of this first implicit this argument and write 1 template. And if you then call this member function, it's going to deduce for you what the type of self is. And that includes whether or not it's const or non-const or ref, okay? And because it's just a function template, the only difference is this keyword this there at the beginning, which we're using to mark this as kind of the this argument. You can also use this other syntax. If you don't need to name the type self, you can write it like this, right? So it's just kind of regular parameter declaration syntax at this point. And it turns out that this is really, really, really cool. So one problem that this solves is that it solves a lot of duplication, or maybe even quadruplication. So it turns out that you actually have to write these overloads in some cases. For example, if you have optional and you want to implement value, you end up writing all these 4 overloads because you need that member function to work in all these cases, depending on what this object is, and you need to write it 4 times because they all have different return values. But it turns out that the body of the function is pretty much the same in every single time, right? So you end up writing the same function body 4 times, which is not great. And there's not really a good way in C++20 and before to fix this. So instead of writing it 4 times, you can say, OK, you write it once, and you declare one of the 4 overloads to be like the implementation, and then the other 3 kind of refer to it. But then because the parameter types don't match and the return type doesn't match, you kind of end up with these ugly casts. You can move this to some kind of private implementation member function, and all 4 overloads refer to that one. Or, which probably is what most people are going to end up doing, you just omit some of these 4 overloads. And that's really the worst option, because then you're going to either lose const correctness, or you're going to lose performance because you're going to make unnecessary copies, or both. Well, it turns out in C++20 we don't have to do it like this anymore. And it's enough to write 1 member function template and template it on whether or not self is ref, const, non-const. And then the compiler is going to deduce it for you, and then this function body just works for all these cases because you just template it on that. Okay, so this is the whole implementation, and it's doing everything the 4 overloads were doing, but it's obviously much shorter and much more elegant and much less error prone as well. So this is the first problem that deducing this solves. The second one is it simplifies CRTP, which is the currently recurring template pattern. Now, CRTP, I'm sure many of you are familiar with this, has been around since the 90s. The term CRTP was coined in 1995 by Jim Coplin. The concept actually has been known to type theorists since the 80s. They call it F-bounded polymorphism, which is a generic that's parameterized on the type that it actually is. And this is a very powerful technique which can be used in various cases. One of them is something like this. Right? So let's say you have some kind of strong type def, right? A counter, but you don't want to just use an integer type. You want to wrap it into some kind of class, so it's kind of a strong type. And then, because it's a counter, you want to increment it, right? So you add these pre- and postfix increment operators, and then in the private bit, there's some kind of underlying representation, which is probably just an integer. It's not really important here. And then you can use it, right? You can take this counter and you can instantiate, you can increment it by calling these operators. And now let's say we have some kind of completely unrelated other strong type. Let's say it's the age of somebody and it has a slightly different interface. You can initialize it with some value, but you also want to be able to increment it. So you end up adding the same operators with the same implementation because under the hood, it's kind of just an integer, right? So again, you end up duplicating code. And so what CRTP, the classic CRTP pattern that's been around since the 90s, lets you do is it lets you get rid of this duplication by writing a mixin class, right? And what you do when you write a mixin class with CRTP is you implement these operators in a base class. And that base class is a template, which is templated on the class that is going to be deriving from it, right? So the base is templated on derive. And now what you have to do if you want to derive from incrementable and inherit this functionality is you need to inherit from it and then pass yourself in as a template parameter, right? So that's the first weird thing. You know, when I was learning C++, I could never remember, do you template the base in the derived or do you template the derived in the base? It's kind of a bit not obvious. And the other not obvious thing is that now you can kind of access derived functions from within base. So it's a little bit like virtual functions, except it's all resolved at compile time. But in order to do this, you need to write this weird incantation. You need to do this kind of static cast to derived. And if you do all this, then it works. And this is a very, very powerful technique. So this is used even in a standard library. For example, std enable this, enable shared from this works like this, right? It uses CRTP. But there are a few problems with this, right? So for example, it is quite easy to make a mistake. There is a bug on this slide. Does somebody see the bug on this slide? Victoria? All right, so we inherited from the wrong type there, right? So this can easily happen if you just kind of copy paste code. Turns out, if you do this, it compiles. And it runs. And it does something, but probably not what you intended because it's undefined behavior, right? And there are different ways to fix this. One thing they can do is you can make the constructor of the base class private, and you can make the derived a friend, and now you're going to get a weird long compiler error there. So it does work, and it's a very powerful technique, but the ergonomics of it arguably are not that great. And so let's see if we can simplify this with deducing this. So first of all, we can now pass this argument into the function. And I'm just writing auto here, but it's a template, right? And the cool thing about deducing this is that if you have this template, which is templated on this, the compiler is going to deduce the type of self for you, but it's actually going to deduce the statically known most derived type, okay? So that means that the type of this auto self in there is actually going to be derived. So you don't have to do any static cast to derived anymore. It's already going to be derived. That's the type that the compiler is going to deduce for you. And if you do that, it turns out that you don't actually have to make any of these classes templates. And so this template stuff just all kind of goes away, and what's left is this. And this is much, much simpler, and it does the same thing, but it's now kind of much more straightforward what's going on there. So deducing this simplifies CRTP quite significantly, makes it much easier to work with it. I want to mention two things that Ben didn't mention in his talk last year. One is it doesn't work in all cases. There are still cases where you need the classic CRTP. For example, if you're dealing with hidden friends as opposed to member functions, which is something you have to do for certain operators. Deducing this doesn't work with hidden friends because they're not member functions, so there is no this to deduce anything from. And another kind of weird thing about deducing this, which actually Daisy pointed out to me recently, and we had quite a long discussion about that. Thank you, Daisy. Is that you can now, because the base class is not a template anymore, you can now form a reference to base, in this case incrementable, and it's going to bind to an object of derived. So it now looks like runtime polymorphism, right? But it doesn't work, because if you then actually try to do anything with this reference that depends on the functionality in the derived class, you get, again, a weird error message. And so it kind of looks like polymorphism, runtime polymorphism, but it isn't, right? And the type theorist would say that f-bounded polymorphism, deducing this replaces intrusive uses of f-bounded polymorphism, where you kind of use derived functionality from the inside, but it doesn't replace non-intrusive uses of f-bounded polymorphism, which is where you use the derived functionality from the outside, which is what we're trying to do here. So there are ways to kind of make this, like avoid this error, right? And Daisy actually was showing me like a few ways we can do this with concepts or whatever, but I would say best practice on how to do this is still emerging, so I still don't quite know what the best way around this is, but I also think it's kind of a little bit of a bogus argument, because incrementable ref here is not really a base class that is useful on its own, right? You wouldn't have an API that takes an incrementable ref. Typically, these mix-ins are chunks of functionality that you want to mix in, but they are essentially implementation details, right? So they're going to probably live in some kind of detail namespace or something. So it's not something that I think you're very likely to run into in practice. I don't think it's actually a problem, but it's worth keeping this in mind, because deducing this here behaves different from CRTP. And so just a couple more things. With deducing this, you can now also add concepts or constraints, right, on a member function. So now you can constrain a member function on properties of the object itself that you're calling it on, which is not something we could do before in C++. And you can also now pass this object by value to its own member function. And this is also something that we were not able to do before in C++. And both of those things enable like really cool new programming patterns, which I unfortunately don't have the time to talk about, but watch Ben's talk. He has a few very interesting code snippets in his talk, and I hope there's going to be more talks about this. So this is really cool. I just want to quickly mention a third problem that deducing this solves, which has nothing to do with those, which is we can now write recursive lambdas really easily. And that's super, super, super cool. So let's figure out how to write a recursive lambda. And I'm going to use a factorial for this. This is kind of the canonical thing that you do with recursion. Obviously, don't actually implement factorial like this, but I think it's a good toy example. So let's take recursive factorial and try to write it as a recursive lambda, right? So this is kind of the naive approach, right? Can anybody tell me if this code is going to compile and work? No. OK, what's the problem? Yes, you're using f. So you're using f inside the body of the lambda, but f doesn't exist yet because you're still in the initializer of the f, right? So you create the lambda expression, then you assign it to f. But inside the body, the f doesn't exist yet. So you can't refer to a variable within its own initializer. That's like not a thing. So we could, we could cheat. We could make this a std function and then capture it by reference. And that actually compiles and runs and does the right thing. But it's kind of not great, right? Because that function has type erasure. It has indirections inside. It's probably going to be a heap allocation in some cases. It's like all this overhead. We don't want to do this. This is not very efficient. So another thing we can do already in C++ 20 is, so we cannot name the lambda within itself, but we can make it that a parameter, right? We can say that the lambda is going to take a parameter, and that parameter is going to be the function that it's going to be calling recursively, right? And then what we can do is we can pass the function to itself when we call it. So this works in C++ 20, but it's kind of weird, right? It doesn't look like a normal function call because we always have to pass the function to itself and then also pass like the other arguments. But probably you kind of can guess now where this is going. But deducing this, we don't have to explicitly pass an object to itself because we can just use the implicit this parameter, because the body of the function is going to be turned into operator paren, which is an inline member function of the closure type. And because it's a member function, it has an implicit this parameter. And we can use deducing this on it. So we can now just write this autoref self, and that's going to be the lambda itself. And now we can just call it within itself. And at the call side, we don't have to pass anything anymore. It looks just like a normal function call. So we can now do recursive lambdas. This is super cool. You might think, OK, but this is kind of a toy thing, right? Why would you ever do this in practice? And there is a really cool example from Ben's talk that I want to quickly reproduce here. This is really cool. So what we're doing here is we have a binary tree. And we're doing a kind of binary tree traversals, classic C++ interview question. And what you want to do is you want to count the number of leaves in a tree, right? So we implement the tree as a variant here. And now we can do this thing. This is kind of a trick. You can find it on CPP reference and in other places. And I've talked about this in my Lambda talk as well earlier this week. You have this aggregate here, which inherits from a bunch of base classes, and you inherit the operator paren. And then you can instantiate one of those with a bunch of lambdas, and they're going to act as an overload set. And as soon as you have that, you can plug that into the variant by doing std_visit, right? And then it's going to call this overload set on the variant, and it's going to call the right overload depending on what the variant is, right? And so we have one overload for leaf, which is trivial, right? If it's a leaf, it has one leaf, so we just return one. And if it's a node, we're going to say, OK, now you're going to recurse, and we're going to say we're going to count the leaves in the left child node and plus the leaves in the right child node, and then it's going to be the leaves of that node. So that's overload here. And the cool thing is that deducing this, because it deduces the statically known most derived type, the self inside that lambda is not the lambda itself. It's actually the fully derived object, which is the whole overload set, right? So it recurses into itself, but if then it finds a leaf, it's going to actually call the leaf overload on it. And that's why the recursion here works. So I think this is a really cool way to implement recursive binary tree traversal. So if you, next time you're sitting in a C++ interview and you're asked to do binary tree traversal, you can write this and you're going to really impress your interviewer. However, I do hope that when you do that, you have a cutting edge compiler, because otherwise this is not going to work. As of right now, the only one of the 3 big compilers that supports deducing this already is the Microsoft compiler. So there you can already do all of the stuff. Hopefully GCC and Clang are going to catch up soon. But yeah, hopefully I convinced you that deducing this is awesome. And now we come to the second section of this talk, which is std expected. Excuse me. It's quite dry in here. All right, so std expected is really cool as well. Std expected is a paper that has been in development for quite a few years, just like basically all the 4 features that I'm talking about today. The first revision of this paper is from 2016, and it has been through 12 other revisions before we actually standardized it. And the idea actually goes back even further. It actually goes back to a talk by Andrei Alexandrescu from 2012, where he already presented this idea. And the reason I think this is so important is that error handling is one of those cross-cutting concerns, right? So every C++ developer working on anything needs to worry about error handling at some point. And there are many different ways to do this, and they have different trade-offs. And lots of different talks have been done on this topic by many different people. Just want to point out a series of talks that Phil Nash has done, kind of looking at all the different aspects of like different methods of error handling, which I really liked. So I'm not going to basically talk about all of this in huge breadth here, but I want to talk a little bit about how std expected fits into the different error mechanisms that we have in C++, standard C++ today, and why it's so important. So here's a simple example. What you want to do is here, you want to parse some code. Let's say we are writing a Lexa for JavaScript. Yeah, completely kind of artificial example, but it's going to be useful. So we are passing a string view, and this is some code, right, that we want to parse. And then this function is going to take this string, and it's going to parse it as a numeric literal. And let's say we only have doubles. We don't have integers. And so what we're doing is we're taking the string, and we're parsing the beginning of the string as a double, and we're going to get the double value out of it. And we're not going to write this by hand. There is actually this very handy function in the standard library called std_strtod, which you've never heard about this. Now you have. It's doing exactly this. So it's going to parse the string, and it's going to return the numeric value. And then it's going to advance and then the next thing that we're going to do is we're going to advance the begin pointer of the string view to kind of the character after this numeric literal. So then the next function can keep parsing something else. And then we're going to return the value. And on the call side, we now have a string. This is our code that we want to parse. And surprise, it's not a number, it's something else, meow. And we're passing that to our function, and we're printing the result. And yeah, what is this going to print? Or what is this going to do? It's going to print 0. Because turns out that std, when it encounters an invalid characters, it's just going to return 0. So you can't really distinguish between, the user actually wrote a 0 and it's actually 0, or the user wrote something that's not a number. You cannot distinguish between these two cases. So we need some error handling. So std actually sets the kind of end iterator that you give it, a pointer, to kind of the end of the bit that it parsed. So if it didn't do anything, it means it didn't parse anything. So we can catch that. And kind of the first go-to error mechanism in C++ is exceptions, right? This is the default way to do error handling that kind of is the first thing that we probably want to do. This is a standard error mechanism that we have. And so we can throw an exception here. And we can also throw another exception if we encounter another error case. For example, the numeric literal is like too big. It doesn't fit into the representation of the double. And then std actually is going to return us an error value, which we can again catch, and we can throw an error. And on the call side, we can catch this error using a try-catch block. So exceptions are great, right? They have lots of good properties. So one of those is that the error path is now very cleanly separated from the happy path, right? So you don't have to change the function signature. You don't have to change the return type. You just do a regular return if everything's fine. And then kind of the error code and the error handling code, they're kind of very cleanly separated from that. There's also a downside though, right? So, there've been a lot of talks about this kind of stuff. The problem with exceptions is that they're doing stack unwinding. And if it's some kind of fatal error and it happens only very rarely, and if it happens, then you must stop everything that you're doing and roll back and do something else, then exceptions are great. But in this case, it's not really that great because this is not a rare fatal error, right? This is something that's going to happen very commonly. It's very easy to recover from. We always want to handle this locally. So we don't need all the stack unwinding stuff, right? And the problem is that with exceptions, the happy path on modern architectures doesn't really have a runtime overhead. However, the error path does have a runtime overhead, right? Because we're doing all the stack unwinding, and it also has an overhead in space because we need to store all the information. We need to unwind the stack, so the binary is going to get bigger. And if you're on a very constrained embedded system, that's going to be a problem as well. And most importantly, throwing an exception and catching it is going to potentially involve a dynamic memory allocation. And that means you cannot ever do this if you're in some kind of low latency or real-time context where you have a hard deadline and you need to only call code that has a deterministic runtime. And so for all of those reasons, exceptions are just not great in this particular case. And actually, community surveys consistently show that about half of all developers work on a code base that doesn't use exceptions. So let's look at some alternatives here. We could obviously always do this kind of thing where we use an error code, right? So we can just return an error code from this function, and then we can handle the error by checking the error code. And now this is great because we got rid of all the kind of performance overhead in the error path. So this is going to be very, very efficient. But it's not very clean, right? Because the error handling now takes over the return value. And now the actual return value, you need to pass it as an in-out parameter. So it's kind of hard to reason about. So this is what that looks like. What else do we have in the standard? So since C++17, we have std-optional. And std-optional is really, really great if you have either a value or if you don't have a value, and it's either not important or obvious why you don't have a value, right? But in this case, it turns out it's just not a great error handling mechanism because we can return an optional from this function, right? And then we can, on the call side, we have a bool operator. We can check if there's a value. If there is, we can dereference it. If there isn't, well, what do we do now? We don't have any information about the actual error. But here we have two different error cases, and maybe we want to tell the user Was it an invalid character, or was it like a huge value, or what was going on? You want to tell the user the error, but we lost the ability to propagate it. And that's exactly where std_expected comes in, right? So now, what you can do is you can use expected, and where optional is either a value or nothing, expected is either a value or an error, right? And so now we can return this std_expected. Looks very similar to an optional. You use it very similarly. You can just return a value. You get implicit conversion from the value to the expected. So the happy path, there's no syntactic overhead. There is a little bit of syntactic overhead in the error path. If you want to construct an error, you need to explicitly use the std_unexpected function. And on the call side, just like with std_optional, you have a bool operator, so you can check if there's a value. But now we have this new thing. If there is no value, if there is an error, we can call the function .error to get the error out, right? And now we can handle the different errors, and we didn't lose that information. And actually, the error type here can be whatever you want. It can be an exception type. It can be your custom error type. It can be just a string with an error message. It's completely generic, right? So you can have an expected void and error, but you cannot have an expected T void. So it needs to be a non-void type, but it can be whatever you want. And this is kind of the API. So we can construct it from a value. We can default construct it if your value type supports default construction. We construct an error state with the std_unexpected. We can compare it to bool. We have this .value, .has value, which does the same thing. And then we can get the value out, either by dereferencing it, and if it's a class, you also get the arrow operator, or by calling .value. That's the checked version. It throws an exception if it fails, and we also have .value or. So far, this is exactly like optional, but then now we also have this other function here, which is .error. And this way we can get the error out. And so this is really cool. But it's kind of not really, I mean, these kind of types, I think every application framework I've worked with had something like this, right? So it's not a completely new idea. But what is new is that it's now in the standard library. And now it is a type that different libraries and different code bases can agree on, right? So it's going to become a vocabulary type. So I actually expect that std_expected is going to be used quite a lot. And now that it's a standard vocabulary type and different code bases can agree on, this is the type you're going to use for this, you can do monadic error handling across API boundaries and like across different libraries. And this is super, super, super cool. And let me just show you why this is cool. So let's say we have a vector of ints. And we just want to compute the sum of all these ints. So we just call std_accumulate, right? This is how std_accumulate is implemented. And we just sum it up, right? Because this is something you can do today with the STL. And now what you want to do is you want to, you're working with signed integers here. And signed integer overflows undefined behavior, right? So you want to catch that. And what you want to say is if our integer addition overflows, you want to catch that error and you want accumulate to short circuit, right? And stop doing what it's doing and is returning that error to us. And how can we do this today? Well, it turns out today, the only really thing you can do is if you're working across library boundaries, is you can throw an exception, right? So you can say, you can pass a custom addition operation to accumulate, and you can say, okay, we're going to pass our custom lambda in there. That's going to be the operation, the addition operation. And in there, we're going to check for integer overflow and underflow. And if those things happen, we throw. And this is the only way you can make accumulate actually short circuit. Because otherwise, it's just a hardwired loop. It's going to loop all the way to the end of the range. But as we saw, there are quite a few scenarios where exceptions are just not a great solution because of the kind of overhead that it produces in the error path. But with std_expected, what we can now do is we can write our lambda with the custom addition operation, and now we can return a std_expected from it. So we don't return the sum, but we return a std_expected. And then if we encounter these errors, if we have integer overflow, we return a std_unexpected with that error. And now we can change our implementation of accumulate to take this lambda as it did before, call the operation, but now check whether the operation returned the value or it returns an unexpected. And if it returns an unexpected, we can now short circuit from the accumulate. And the really cool thing about this is that the accumulate at the top is completely agnostic to the particular error type that you used. Notice that at the bottom we're using a numeric error, but that type doesn't occur anywhere at the top. So it's completely generic to like the particular error type that the expected uses. And the only slightly ugly thing is we have to do this little bit of meta programming here where because the return type of the lambda can be different from the return type of the accumulate, we kind of have to take the lambda, extract like the return value, extract the error code from it, and construct a different expected with the accumulate value type and that error from the lambda in it, right? So you end up with this like slightly ugly piece of meta programming, but the only reason I wrote it like this is because I needed it to fit on a slide. You can actually extract it out into a meta function. You can give it a nice name, and then it's going to look a lot less ugly. And this way you can do this kind of monadic error propagation across API boundaries. And here's another example. Something that is really, really cool that you can do is you can use an expected of value and a variant of different errors, right? And this is really cool because then you can have different layers of your code returning different errors, right? So for example, you're doing parsing and you have one place in your code that returns a parse error, and then maybe somewhere else it returns an IO error as you couldn't read. And so you can kind of collate these different errors into a variant and pass them up to the code that's actually going to handle it. And then at the call set where you handle this error, because it's a variant, you can visit it, right? So you have at the beginning the happy path, which is just the usual expected thing. You check it, and if it's okay, if it has a value, you can just dereference it. And in the error path now, you can do a std visit on this variant that contains the error, and you can add different lambdas that handle the different errors. And so now it looks a lot like kind of a try-catch block here, except that it doesn't, again, have any of the runtime overhead in the error path that exceptions do. And it has another really cool property. You get a hard compile error if you omit any of the lambdas here. So if you don't handle all the variant cases, you're going to get a compile error. So it's checked at compile time. And that allows you to do really cool things like, let's say you have another layer somewhere in your code, and you introduce a new error type. And now you want to return it kind of all the way up the chain. And then if you introduce this new error type, you get a compile error all the way up the chain. So you need to add this error to all the variants until you get to the call set here. The call set where you handle the error. And there, you also get a hard compiler error. And the compiler forces you to add this case, right? Add a case to handle this new error. And you can either handle it right there, or you can rethrow the error by returning an unexpected to like the layer above. So this is super cool. And this is actually quite similar now to Java checked exceptions. So I want to be diplomatic here. It's not universally agreed that this is like the best error handling mechanism ever, but there are cases and there are use cases and code bases where this will be a very good, very useful error handling mechanism. And so I think it's really, really cool that we can now use all of these techniques by using a vocabulary type that is in the standard and that everybody can agree on. So that is really cool. In C++26, as expected, it's going to get even better. So this is a paper that didn't quite make the feature cutoff deadline for C++23, where still expected is also going to get kind of these monadic functions and then or else, etc., which std optional already has. So I guess we're going to get this in C++26, and that's going to make std expected even more composable. So I'm really excited about that. All right, we're done with std expected, and let's move on to the third part, which is mdspan. And I'm going to just quickly have another sip of the water here. And so mdspan, I have to say, is my personal favorite. This is my personal favorite feature of C++23, and I need to be completely subjective here. This is the paper. It's been in development for something like a decade. It has lots of authors. They've done a lot of work to get this into the standard, and I'm super, super excited that we finally voted it in. It just made the deadline, and we have it in the standard now, and I'm super excited about this. Why am I excited about it? So I need to tell you now a little bit of a personal story. This is a picture of me many years ago. This was before I was working on any IDEs. This is before I was working on any music software. This was before I knew about anything about C++. I was at the time working in astrophysics. This is the Astrophysics Institute Potsdam in Germany, where I was working at the time, doing my PhD. And the kind of stuff I was working on was this. So we were doing these numeric simulations of cosmic structure formation. So we were interested in the structure, the large-scale structure of the universe. And by large scale, I mean galaxy clusters and bigger, right? So we were looking at really big scales. We're talking hundreds of millions of light years here. And so we were doing these numeric simulations, and the way this worked was that we took the universe, we took like a box, which was maybe, I don't know, 100 million light years across. And then we discretized it with on a 3D grid, okay? And we discretized the kind of physical quantities that we were interested in, density, velocity, temperature, that kind of stuff. And then, because the universe has no bounds, but a box has bounds, we apply periodic boundary conditions, so it's kind of like tiling. And then we create some kind of random number field which looks like the early universe, and then we program in the kind of numeric differential equations for hydrodynamics, like how gas behaves, gravity, and then the third thing is cosmic expansion, because the universe expands, right? And so we throw all this together and we let the system evolve. So we do this numeric simulation, and then in the end we get some distribution of matter, and we look at, does this look anywhere near like what we're actually seeing in the telescope? And if it does, then our theory is correct or whatever. And if you do this kind of stuff, you do need a lot of multidimensional arrays, right? Because we have these like 3D boxes. So you have lots of 2D arrays. If you have like stencils or something, you have 3D arrays. Actually, the most common one is 4D array, because you have the 3D box, and then the fourth dimension is like the quantity you're interested in, so density or velocity or whatever. And at the time, I was doing all of this in Fortran. So Fortran was the first programming language that I learned. I was never meant to become a programmer. I was studying physics, and so Fortran is what everybody was using. So I learned Fortran. That was my first programming language. And in Fortran, working with multidimensional arrays is actually really, really beautiful. So this is Fortran code where we have a 3D array, and we just kind of declare it. We give it the extents. And then we have a loop, and it doesn't really matter what we do here. We just assign some value to every element of the 3D array, which we somehow compute from the indices. Toy example, doesn't really matter. But the cool thing is that in Fortran, multidimensional arrays are native core language data types, right? So they're built into the language. So you can just easily declare them. You can do things like multiply the 3D array with a number, and it's going to multiply every element with that same number. You don't have to write a loop or anything like this. You can print out the whole thing in one statement, right? So this is really funny. We now got formatted output for ranges in C++ 23. Fortran could already do it in the 60s. Okay? So this is really cool. It's an array where we know the bounds at the extents at compile time. Maybe we want to initialize a dynamic array where it's on the heap and the extents are runtime, so we can just say it's allocatable, and then we can just allocate it and give it the runtime extents at runtime, and it just works. We don't have to deallocate it, like it goes out of scope and deallocates things automatically. So working in Fortran with multidimensional arrays is really, really, really beautiful. And then I switched from a project using Fortran to a project that was using C. That was the only other language that people around me used kind of in that field at the time. And in C, working with multidimensional arrays looks something like this. This is a static array, right? So this is still okay. But if you want to do a 3D dynamic array, this is how my supervisor taught me how to do this, okay? So we have to declare the array now as a pointer to pointer to pointer. We now have to malloc each dimension kind of separately, and it just breaks my brain. I can never remember how to write this loop correctly. Then this is the loop where we actually do anything meaningful, and then we have to, at the end, free the data again per dimension. And this is kind of what we have to do. This is the pattern that was all over the code base that I was working with. Much later, I learned this is actually not a great way to do this, even in C, right? So you have two problems here. First of all, every element X is going to be a multiple dereferences, which is not great. And probably this is also not going to be contiguous in memory. So that's the other reason why it's not great. So we can do something slightly more clever. We can allocate a 1D block, right? And then we can just pretend it's a 3D array, even though it's not. And you can write a loop with the 3D indices, and then index into the array using this formula here, where we kind of compute the 1D array element index from the 3D indices that we're using in the loop. And this is kind of the formula to do this. And this is how we do it in C. In C++, of course, we can do better than that. We can put this whole thing into a class. We can template it on the element type. And then we can hide this access formula here behind operator paren, and we give it the 3 indices, and it's going to just return a reference to the element. Who here has written a class like this? OK, that's like half the room. I have written a class like this, I think, 5 times. And it gets really fun if you actually then want to template on how many dimensions this has, right? So then all your functions become varied templates. And it becomes even more fun if you want to optimize. If some of your array bounds are known at compile time, you want to get the optimizations, right? So then everything becomes const expert and becomes even more fun. And it's really, really, really hard to do. And the cool thing about mdspan is that they basically solved all the problems in this space. And it's now in the standard. How amazing is that? So here is an email that Bjarne Strostrup wrote to the committee mailing list some time ago, and he gave me permission to put this on a slide here. And he was saying, can anyone recommend a quiz tutorial for mdspan? And he followed it up with an email saying, what I really like is a short introduction for non-experts. So here's my take. Let's say you have this 1D block of data, and it doesn't really matter where it comes from. And what you can now do is you can wrap it with an mdspan. And you give it the pointer to the data. And then you give it the extents of your dimensions, right? And so in this case, you have 3 dimensions, so we give it 3 extents, and those are going to be the sizes basically in every dimension. That's what the extents are. And then we can write our loop, and we can use the mdspan to index into the elements and do our work. And so there are 3 things that are important about this. One is mdspan heavily relies on ctad. So it has a bunch of template parameters, but you don't have to write any of those. So ctad is class template argument deduction, which is a feature we had since C++ 17. You don't have to write any of these template parameters because it's just going to deduce, OK, so you're passing at a pointer to double, so our element type is double. And you're passing it 3 extents, so I'm going to be a 3D mdspan with those extents, OK? So it's going to do all of this automatically using ctad. The second interesting thing is that it's now using the syntax with the square bracket operator. And this is a core language change that we did in C++ 23 for mdspan. But obviously, now that it's in the language, you can use it for other things as well. The square bracket subscript operator can now take multiple arguments. So you can now give it like 3 indices. And this is really neat syntax, I think. This is really expressive. This tells you, yes, this is a subscript operation. It's not a call operation, right? You're indexing into something, and you can now do this in multiple dimensions. So this is an example how a core language feature kind of emerges for like supporting a library feature, which is kind of cool. And then the third interesting thing about this is that mdspan is non-owning. So it doesn't own the actual data. It doesn't matter where the data comes from. It just wraps it. So it's literally like std span, except for multiple dimensions. And that means that you can have another mdspan wrapping the same data and looking at it in some other way. So here's a 2D span with a different shape, which just looks at the same data, and that's totally fine. And you have this .rank member function, which is telling you what the dimension of how many dimensions the mdspan has. There's also different ways to give it extents. So we already said the extents can either be known at compile time or they can be known at runtime, right? And depending on that, if you know the extents at compile time, you want to get the nice optimizations, right? And you can also mix and match kind of compile time and runtime extents. So you can create your own extents object. And in this case, It has a bunch of template arguments. The first one, the int, is actually the index type. So that's not the element type. That's still double. This is the index type, right? So it's going to be an integer type. But you can also use a signed integer here, which is really cool. But that's another topic. You can give it then the extents, and you say, OK, first dimension is extent 4, second is extent 4, and the third one is dynamic. And then you give it the extent of the dynamic dimension at runtime using a constructor argument, and then you pass this extends object to the mdspan again as a constructor argument. This is one way to write this. Another way to write this is you can bake it into the type of mdspan, right? So now you can start writing template parameters for the mdspan. You can say it's an mdspan of double, and the second template argument is this extends type. So you can kind of bake it into the type like this, and then what you can do is there's, again, two options here. You can either pass just the one dimension here that is dynamic, or however many are dynamic, just the extents of those dimensions into the constructor, or you pass all of them into the constructor. And both of those will work. In the second case, you need to be careful that you pass the same extents for the static ones as you did before when you declared the type. And there's also a handy type def. If all the extents are dynamic, turns out you have to write quite a lot. You have to spell out std dynamic extent 3 times. And so there's a handy type def for that. You can write std d extents. That means all the extents are dynamic. So you just give it the index type and then just how many dimensions you have. And then all of them are going to be dynamic. And then you're going to use that extends type. So I think this is really kind of straightforward. Turns out mdspan actually has 4 template arguments. The first one, as always, is the value type. The second one is the extents. We talked about this now. And there's a third template argument, which is really interesting, and that's the layout policy. And the layout policy is how the indices that you put into the square bracket operator, how they map to the index and the actual data. So that's like the formula, right? And it turns out there's different ways to do this. So in C and C++, if you have a multidimensional array, the default ordering is row major order. If you use Fortran, the default is column major order, which is like the opposite way around. And mdspan has names for these. It calls them std layout right and std layout left. I was actually, in the beginning, quite confused about this. I was like, why do they not call them std row major order? That's the term that everybody knows, right? But then Daisy Holman, one of the authors of mdspan, pointed out to me that it actually makes a lot of sense, and I think this is really cool. So row major order. Which dimension is the fastest running one, the one that's contiguous? Question. It's the rightmost one. So therefore, layout right. If you have column major order, which dimension is the one that's contiguous, the fastest running one? It's the leftmost one, so it's layout left. I think that makes a lot of sense. So if you use the layout right, this is the default. We get the usual ordering that we get in a C and C++ array. You can check it. There is the member function called .stride, which tells you the stride of every dimension. And you see that the last dimension, the rightmost one here, has stride 1. So that's the contiguous one, okay? And if you do layout left, this is what you do if you're working with an array that came from a piece of Fortran code. Then it's the opposite, and then the first dimension is the one that has stride equals 1, and that's the one that's contiguous. And then if you work with that, then if you want to loop through that in C++, you need to remember to invert the loop indices and do the loop the other way around, right, inside out, because otherwise you're not going to be looping contiguously in memory, and that's going to be slow. So we have a bunch of standard layouts in the standard, but the cool thing is that you can actually, this is a customization point. You can create your own layout policy. You can just plug that into mdspan. So those two are not the only things you can do. You can, for example, if you work with image data, you might want to use some kind of tiled mapping like this, right? If you're looking at only a portion of your 2D image at a time, this is probably the most cache-friendly layout, something like this. So you can have a layout like this, just plug it into mdspan, it just works. You can have even a different one. Here's yet another way to map multiple indices to one index. It's a Hilbert curve. Here's a 3D version of the Hilbert curve, and that's actually something that we were using back then when I was doing astrophysics. We were using that in our simulations, and I had to write all of this by hand, and I wish we had mdspan back then because it would have made so much easier. So this is really powerful, and you can do even more stuff with these layers. They don't even have to be contiguous like these. They don't even have to be unique. So you can even map different sets of indices to the same place in memory. For example, if we have a symmetric matrix where the top half and the bottom half are the same, it turns out that it's enough to store just the bottom half, and it's going to save you a lot of space. And whenever somebody indexes into the top half, you can just remap them into the bottom half, right? So that's a non-unique layout. And this is kind of simple enough that I became curious, and I was like, okay, what would it take to actually write this layout and plug it into mdspan? How can I make this work? So I went ahead and I tried to actually implement this, and I took basically just the paper, the mdspan paper, and the reference implementation that's on GitHub, the Cocos one. And it took me about an hour to figure this out. So it's not black magic. It's actually relatively simple. And this is what I came up with. And this actually does compile and work and everything. So what's going on here? This is our layout. So the layout always has to have this template in there called mapping. I now here constrained it on that it needs to be two-dimensional, because I only care about two-dimensional matrices here. And then the next thing is that it has this constructor where you pass in an extend. And I'm doing something a bit more clever here. So I want to check that the two extends are the same. So I want to check it's a square matrix, right? Because if it's not a square matrix, it can't be a symmetric matrix. So I need to make sure that both extends are equal. But then I can actually check at compile time, are both extends known at compile time? So that's the rank underscore dynamic tells you how many extends are dynamic. And if that's 0, then they're all known at compile time. You can static assert in that. And otherwise, you have to do a runtime check. And then this is where the magic happens. This is the operator paren of the mapping type. And that's where the magic formula goes, how you actually map from the indices to the element. And this happens to be the formula for symmetric matrices where you store the bottom half, right? So you kind of, if you're in the upper half, you kind of swap the indices, and then you index into the lower half with this particular formula. And then you just have to write a little bit of boilerplate code, but that's all described in the paper. So you have to tell mdspan what the size of the underlying memory is. So that's the required span size. And then you have to also implement these kind of weird, not weird, useful member functions that are going to tell mdspan if the layout is unique, if the layout is exhaustive, which means that every element is visited, and whether it's strided or somehow irregular. And so if I do all that, I plug it into mdspan, and it just works. And I tried it out, and this code that's on the slide is going to compile and run. Now, if you want to be super clean and you want to stick this into a library, you want to probably do a little bit more stuff. You probably want a copy constructor and an assignment operator and an equality operator and all that stuff. And I didn't add that here because my particular test code worked without it, but probably if you want to do something more interesting or more complex, you probably want to be adding those for completion. But it's all pretty straightforward stuff. So that's layout. There's also a fourth template argument here, which is the accessor. And that is also really cool. So this is once you found the element you want to access, how do you access it? And the default is basically just return a reference to it. But there are other interesting things you can do. You can have a custom default accessor that accesses the element by std atomic ref, if you want to do this atomically lock-free for multiple threads, or people use it to access GPU data. And this is the kind of thing where an accessor for a non-owning type is a little bit like an allocator for an owning type, right? So most of the time, you don't really care about it. You're going to just use the default. But if you need to customize it, you really, really need to, and it's going to be super useful. So there are now a few talks already about mdspan that go into a little bit more detail that you can watch if you're interested in kind of more nitty-gritty details or how to actually use it. There's one that Bryce Edelstein-Lelbach did in July at C++ North. So he talks for about an hour on mdspan, and he talks a little bit more also about how to use it with algorithms and why mdspan doesn't have iterators and how you get around that and how to use it in generic code and stuff like that. Nevin Lieber also did a talk earlier this week about mdspan, and I think there are a couple more by now, so you can learn more about mdspan. I think that's really, really cool. One last thing I want to say is that there's another paper here on the way for C++ 26, which is mdarray. That's kind of the owning version. So MD array is to mdspan, pretty much what vector is to span. And we're going to get that in C++26, hopefully, if nothing goes wrong. However, I'm really happy that we standardized the non-owning version first, because that's the more generic one, right? If you're working with an array that came from somewhere else, like some Fortran code or whatever, it's not going to be very useful if you only have the owning MD array, but it is very useful if you have the mdspan, you can just wrap it, right? So it doesn't matter where it came from. Right, so this is mdspan. Hopefully I convinced you that it's really, really cool. And now we're already almost at the end, and this is the last section of the talk. And we're going to talk about stat print. And this is the brainchild of Viktor Zverevic, another paper that has been in development for quite a while. You see it's been through 14 revisions. And this paper and this feature that we now have in C++23 is literally going to change the world, because it's going to change how we write hello world. Okay? So hello world, you can open any C++ programming book. I'm just open. I had Bjarne's one on my bookshelf. And this is literally the first code snippet in that book. So first there was the empty main. It's kind of boring, but like the first code snippet in that book that does actually anything meaningful is hello world. And I can also go into my favorite IDE and just open a new project, right? And say, okay, I just want some default executable. And this is the default project that I get. And again, it's hello world. So hello world is everywhere, right? This is kind of the default application that just does something. And interestingly, C-line here does something slightly different than Bjarne. It uses std_endl instead of \n, and it also does the return 0, which you don't need in the main. But let's not talk these two issues. Let's just kind of put them to the side, not talk about them, and go back to Bjarne's version here, which is kind of the minimal version. What's wrong with this code? Let's do a code review. There's a few things wrong with this code. So first of all, std_cout is kind of notorious for not having that great performance, right? IO streams, if you benchmark them, they don't really compare very well to other ways of doing output. The second problem is that the API is kind of a bit weird. Like you have this like left shift operator, and you have a whole zoo of IO manipulators. For example, if I want to print a bool, and I just shift it through to std_cout, what is that going to print? 1. Okay, what do I need to do to print true instead of 1? Bool alpha. Okay, you're good. What header is bool alpha in? No, it's in header IO stream. But some of them are in header IO manip. For example, setW, which is the one you need to set this field with, right? So it's not really very easy to work with this or to remember all of this stuff. But that's not even the problem. Like the problem that annoys me the most. Let's go back to the minimal version. So this is hello world in English. And if you do this, it's going to print hello world. However, my first language is not English. My first language is Russian. And I know my accent doesn't sound like it, but I'm Russian. This is my mother tongue. And if I want to write hello world in my mother tongue, what is that going to do? Well, on my Mac here, it's going to do the right thing. But on my Windows machine at home, it's going to print this. And I'm not making this up. I copy-pasted it from what my computer actually did. This is a screenshot. This is what it actually printed. Okay? And this is the kind of stuff, like this is why Python people laugh at us, right? Because in modern programming languages, this stuff just works. In C++, well, what's going on here? So the problem is that you have a source encoding, which in this case is UTF-8. You have an execution encoding, which is probably UTF-8 or UTF-16, depending on the compiler flags that you have used. But actually, none of the compiler flag combinations that I tried resulted in any meaningful output here, because the encoding of the terminal is code page 437. And std_cout doesn't care about encoding at all. It just forwards the bytes to the terminal. The terminal is going to do whatever it wants. Code page 437, that's what you get. So I think that's very, very sad. And we kind of solved part of the problem already for C++20. So in C++20, we have std_format. Std_format actually does handle Unicode correctly. It also does a bunch of other things. Std_format, another paper from Viktor Zverevic, which you got already in C++20, is super, super powerful, right? So It does the right thing here by default, right? For the bool, it does print true. If you do want to print the bool as an integer, you can use, it has this little format specifier syntax. In this case, you do :D, you can print it as a number. And it does everything that printf does, with slightly different format specifier syntax, but it does everything that printf does and more, right? So it does even more. You get support for a lot more types. For example, with std format, you can easily print std chrono, days of the week or whatever, and it just works out of the box. The other really cool thing is that it's actually a lot safer than printf. So printf, if you have a format string and you forget some arguments or you pass it wrong arguments, it's really easy to crash your code or to end up with a security vulnerability because it's all just kind of runtime variadic arguments, right? But then with std format, it's checked at compile time, and if you forget the B here, you get a compile time error. And the other really cool thing about std format is that by default, it doesn't pull in the locale, which is something that's really, really annoying about IO streams, right? So it doesn't by default pull in any locales. You have to give it a locale explicitly, and then it does the right thing. But there's still a problem because std format doesn't actually know how to print anything, right? So you have a way of working with strings which does everything, but you don't have a way of actually getting the string out of your program. And so if you want to do that, we end up with something like this again, and that's just not great, right? Because first of all, we're creating a temporary std string object, which we don't need. We're calling a left shift operator function, member function that we don't need. And then std performs formatted output on a string that is already formatted. So that's, again, a waste of CPU cycles. But stdprint solves all these problems because now in C++23, we can just do this. And it just works. And that's super cool. And the reason it works, if you go to the specification of stdprint in the C++23 committee draft, which is hopefully going to be what's going to be the new international standard next year, there is the sentence here which is saying that if you're dealing with Unicode, then stdprint is going to call the underlying native Unicode API. So it's going to figure out whether you're writing to a file or to a terminal. And if you're writing to a terminal, for example, on Windows, it's going to call the proper appropriate Windows API function that actually knows how to deal with Unicode. So you're getting, whenever possible, consistent glyphs as your output, whatever you're doing. So stdprint is really cool. And the other cool thing about stdprint is that it kind of builds on top of std format. So it uses the same syntax. So you get all the benefits of std format kind of just automatically carry over to stdprint, right? So it prints the right thing for the bool. You have the same format specifier syntax that std format uses. It just works for stdprint. You again get the safety. It's checked at compile time. And if you want to print to another stream, then stdout, that also works. You just give it the other stream as a first argument here. Like, for example, if you want to print a std or something. And so, yeah, that's really great. And that means the new hello world in C++ looks like this. We changed it, except we actually changed it twice, because now we can also import the standard library as a standard library module, which is what Daniela was talking about on Tuesday. So that's even more awesome. So this is the new hello world. OK, maybe not quite. There is another thing here. Stdprint doesn't print a new line at the end, so we still have to do the \n. However, we have a thing for that as well in C++23. We now have stdprint line. And that's going to do the same thing as it does on all the other programming languages. It prints the string that you wrote with a new line character at the end. So I'm actually quite curious which one of the two is going to establish itself as kind of the new canonic way to write hello world in C++. So maybe we can do a little vote here. Who likes the first version? OK, who likes the second version? All right, so that's the vast majority of the room. So I hereby declare the second version the new official way to write hello world in C++. And that's how C++23 changes the way you write code. Thank you. And can I have the slides back, please, for a second? Before I take questions, I want to say one last thing. There were a few people who helped me immensely preparing this talk. They pointed out things that I missed. They taught me things that I didn't know. So I just want to give a shout out to Gaspar, Daisy, Daniela, Phil, and Christian, who helped me a lot with preparing this talk. Thank you very much. Now I'm ready for questions.
Thank you for the talk. We have a bunch of questions online. First one is slide 114. How does that aggregate initialization work?
Ooh. I explained it in more detail in my Lambda talk on, I think it was on Tuesday. C++ Lambda idioms. 114. This one here. So basically we want to inherit from these lambdas and we want to inherit their call operator. And lambdas, the type of lambda is a closure type. That's what the compiler generates for you. So that's a class. So we can inherit from it. We can't name the class, so we can't inherit from it directly, but we can have an aggregate class which inherits from its own template arguments and then inherits their call operator. And then because it doesn't have any private members or anything like this, it's an aggregate. The base classes are its aggregate elements. And so we can use aggregate initialization, that's the stuff in the braces, and then we can give it the lambdas as the aggregate elements, which are the base classes. So it's gonna take the lambdas and it's gonna use their call operator, and that makes it effectively an overload set with those lambdas inside. Okay. Here.
Thanks a lot for the great talk. Regarding state expected, you kind of said that there are some situations in which exceptions are a totally fine way to handle errors, and that this is just an addition in some situations where it isn't really great to use exceptions. Now, I'm coming from a code base where there are no exceptions. So my kind of question is, what is your feeling about, are there really situations in which you would say, this is clearly worse than exceptions and where we would in the future stick with exceptions? Or is this going to be the beginning of the slow phasing out of exceptions over the next 3 decades? I don't know.
That's a good question. I think they're kind of different. I think exceptions have all these benefits that you don't get from library classes. And so I would still use exceptions whenever I don't care about the error path, allocating memory, or having this overhead, because I'm not in a constrained system. I don't care about this overhead because I'm only optimizing for the happy path, which doesn't have overhead. So in all those cases, I think exceptions are still fine. But the other thing is that I'm really curious if you're going to get more language support. Herb had this paper 3 years ago about zero overhead deterministic exceptions, which I think it's kind of dormant right now. But other languages have interesting, Rust, have interesting baked-in language mechanisms for error handling, which also don't have the overhead of kind of exceptions, but they handle it in a language way, which leads to even more composability and kind of elegant syntax. So I think and I hope that this is going to be the future, but it's probably going to be a while until we get that in the standard. So for now, I guess you just need to pick what your use case is. And depending on that, I would pick either exceptions or state expected.
Thank you.
Hi, thank you. You mentioned the cost of IO streams and also the optional manipulation check cost. When you use std print, does it know enough? And I saw in the documentation that flashed by that the first parameter is just an IO stream. So does print know how to secretly avoid some of the cost of the streams themselves?
Yeah, so std print, so I'm not really the expert on this. Let me see if I can scroll to the specification here. But from what I know, basically std print, I'm not thinking, here it is. Std print doesn't actually call the IO streams. It calls the underlying, kind of the underlying thing. So if you look at Victor's papers, he did benchmarks and he found that std print was actually quite a lot faster than IO streams in his benchmarks. So I hope that answers the question.
Yes, thank you.
But caveat, I'm not the expert here. So read Victor's papers.
Thanks.
Another question from online. Are there implicit conversions between span and one-dimensional mdspan?
Ooh, I don't know. Do we have Daisy or Christian in the room?
No, not anymore.
No, not anymore.
They were too complicated.
They were too complicated. Thank you, Daisy. I think we're over time. Can we take these 2 questions or should we stop? Yeah, okay.
Hey, Timur, so
thank you for the talk. I really enjoyed it. So my question is about your example of using stud expected in the parse number. I wonder if you kind of took this example and put it in Godbot or Compile Explorer and saw whether there was any overhead of using the stud expected versus using the output error or return error and output parameter.
So I did not specifically do this with this example, but there are papers who looked at it. I don't remember who it was. It might have been Ben Craig. Wrote a paper about comparing the different mechanisms and actually benchmarking them. So this work, there is work in this area. I haven't done this myself for this particular example.
I see.
But I would expect that there's probably not, an expected is basically a pair of value and error with a different API. But
yeah, so my expectation, I didn't review this as well, but since expected must have some kind of Boolean there to distinguish the error and the value, it seems like there will be kind of difference in the assembly versus when you do just the return error, because you don't have this Boolean anymore, and So
why don't we look at it after the talk and pull up the Godbolt and have a look what the compilers actually do.
I want to be respectful of the time, so thank you.
I'll take one more question online. Isn't stud expected a little too intrusive? If you use it in a function, its caller has to return a stud expected too. If it cannot handle the unexpected error and so forth, so you kind of have to return the stud expected from every function unless one of the functions just unpacks the unexpected error and throws it.
Or handles it.
Or handles it.
Yes. Yeah, I guess this is how you would use it if you want to do this kind of propagation across layers. Yeah, I think the answer is yes. Last question here.
Hi, thank you. Great talk.
Thanks.
Do you think that rasterizing geometric shapes, using the layout policy would be a good use case for, doing something with mdspan?
Yeah, I think so too. So I'm not an expert in this kind of stuff, but actually something I forgot to mention. Something that I found really cool about mdspan is that it just kind of pops up in all these different domains. Like I did a lot of audio in the past and did a lot of talks about that. And if anybody have seen those talks, I talk about things like we have the audio buffer there, and it has a channel layout, and it can be interleaved or de-interleaved, and like all the stuff. And it turns out all of these things that are special cases of mdspan, and you can do all of the stuff with mdspan. And so I think this is probably true for a lot of domains because it's such a generic type that kind of handles pretty much every scenario you can think of. So I'm probably not directly answering your question, but
Get you later.
Yeah, cool. All right, I think we're also over time and I don't see any more questions. So thank you so much for coming. I really enjoyed it. I hope you enjoyed it too.